In the last class, we had discussed the buses which we expect to find or we expect to implement in an SOC. We have also looked at serial buses and we had started discussions on one of these buses, that is I2C. Today, we shall continue the discussions on I2C and look at other serial buses as well. First, let us recapitulate the I2C basics that I had done in the last class. I2C is basically a two-wired bus. It has got two lines, serial data line and the serial clock line. The voltage levels are logically high and 0, that is low. The bit transfer takes place when your SCL is 1. So, SCL 1 implies that SDA line now has a valid data. So, you got to have valid data when the clock is high, and data change can take place, the transitions on the data line can take place when your clock is low. So, basically it is a two-line bus, and using two lines there can be number of devices hanging one after another and they can communicate data with each other using just two lines. So, here the data transfer is in a bit serial fashion, and that is a basic difference with any of the parallel buses that we have seen so far. So, I2C lines can have two possible states, okay? What we say a float high and drive low, and pull up resistor on the line are connected and only devices pull the line low. So, if no device is pulling on the line, it will float high. That means by default the I2C signals will be always high. So, what is really this interfacing circuitry? Here you will find that I have shown two such blocks. If you look at it, that these are the two lines, this is corresponding to the SCL and this corresponds to SDA, the serial data line, and there are two devices hanging from these two lines. So, here the serial clock is connected, okay, and this will be the internal input to the device, and this is the out and this is basically in. So, what does that mean? That means that when it is driving, when this device is intending to drive the bus, the clock should be generated by this device, else it will get the clock in, that is a clock which is currently on this line being generated by some other device. Similar thing is true for the data line, that is SDA line as well. So, these are all open collector interfaces or open drain interfaces. So, you have got the resistors connecting these lines to the VDD, that is drain voltage, so that the normal condition for all of them is high, and effectively this connection is nothing but wired ending. So, a device can pull the line low. This is the basic structure and interface of the devices for connecting onto the I2C bus. Now, when the transmission is to take place, there has to be start condition and stop condition. Start condition is when the SDA line makes a transition from high to low when SCL is high. Okay. So, when the clock is high and SDA is making a transition, it means there is a start of a frame, that is a frame of data that is being transferred. The stop condition occurs when there is a transition from 0 to 1 and when SCL is high. So, these two states, this is S and this is P, the stop condition. There can be also another state, what is called a repeated start. So, start is generated instead of a stop after a frame. So, bus is normally busy after S and before next P, and free after P and before next S. So, this actually indicates beginning of a data frame which is to be transferred. So, what happens in data transfer? Data bits are therefore transferred after start condition, and whole transmission is byte oriented. So, one unit that you transfer is 8 bits, but that is considered as 8 bits data plus 1 acknowledge bit. This acknowledge bit is to be transmitted by the recipient of the data, and the order in which data is sent is that the most significant bit is sent first. In fact, since there are multiple slaves which can be connected onto the bus, we need a mechanism to identify the recipient of the data. So, address of the slave is also data. In fact, the first byte after this transition, when you start transmission, is actually an address. During the first byte, the master is the transmitter and addressed slave is the receiver. And next bytes depend on last bit in the address byte. So, depending on whether it is a read operation or write operation, either it will be master transmitting the data or it will be the slave transmitting the data. The recipient will always generate the acknowledge bit after transmission of 8 bits. So, this is the basic addressing scheme. There are 7 bits which is used for addressing the slave devices. So, each slave device can have a 7-bit address. The 8th bit is basically the direction which tells you whether it is a write or read. Master may generate repeated start, okay, and address another device. That means the bus still continues to remain busy. Each device listens to address. If the address matches that of the device switches state according to its read or write bit, as part of the data which is getting transmitted from the master. So, what is exactly the synchronization takes place? The master sets SCL 0 and generates pulse for each data bit, okay? And 8 pulses for data is to be followed by 1 for acknowledge. So, here master's responsibility is to generate the clock, although the acknowledged data will come from the slave, but master will be generating the clock because it is driving the bus. After acknowledge, the master tries to generate next byte's first pulse. The slave can hold SCL low, okay. So, if the slave holds SCL low, then the master will switch to wait state because it cannot send the next data because device is not yet ready to receive the data. So, that ready condition is now being provided by pulling the clock low. So, pictorially if you look into it, so this is basically the transition which is taking place from 1 to 0 when my SCL is high, which is indicating that a data frame is starting, okay. Followed by this, there are these clock pulses which are being generated by the master, and this data is being sent with the most significant bit first. Now, at this point corresponding to this clock, the master does not send any data, okay. And here actually the whole reason is why master is not slaving, because it is really waiting for the acknowledge to come from the slave. after this, what happens? The slave will pull down the clock, because slave would like to now have a wait state, because it may be using an interrupt, slave may be using an interrupt call to transfer the data or do anything, any other housekeeping task. So, it introduces a wait state here. So, when there is an wait state, effectively no data is sent. Again, the clock starts pulsing at this point, and from this point onwards the data transmission can start. Okay. And here what is being shown is that after that there can be a restart or a stop condition, that is depending on how your SDA line is going through a transition when your SCL is high. So, this is exactly how the data transfer is coordinated by the clock, the master clock. Now, the data bits which flows along your SDL, okay, serial data line, is generated by the transmitter. Now, transmitter can be master or maybe the slave, depending on whether it is a read or write operation. In the 9th pulse, okay, the transmitter releases SDA. The receiver must hold SDA low in order to acknowledge the received data, okay, and slave must release SDA after the acknowledge bit, okay, so that now the master can again start transmitting, provided clock is not pulled low by the slave. So, now if we see the waveform, if it is the same thing, so what you are finding here, this is acknowledgement which is coming. So, this acknowledgement here, the SDA line is now pulled low by the slave, and this is corresponds to this clock pulse which is generated by the master. So, the frame format is, you have got the complete frame format is, you have got the start transition, you have got the slave address, then you have got the read write bit, okay. Then actually you start the address. Now, here A is the acknowledgement which comes from the slave. So, after your first byte which indicates address, you got to have an acknowledgement from the selected slave. If no such slaves exist or currently connected to the bus, then obviously the acknowledgement will not come and the frame has to be aborted. So, this is exactly how the whole frame format looks like, and the master receiver is since the second byte onwards, this effectively similar. So, you have got the data which is getting transferred and with the corresponding acknowledge. Now, I2C is basically a multi-master bus. Okay. So, in that I2C bus, there are multiple devices which are hanging from, and they can take up the role of master or slave in an interchangeable fashion. Okay. So, there could be multiple master which can be there on the bus. So, you need a mechanism for bus arbitration. Now, any one of several different devices which are there on the bus may act at the master as a master at various times. And what you have observed, I think by now, that there is no global master to generate a clock. In fact, the device which is currently driving the bus becomes the bus master, and the master drives both SCL and SDL as the case may be. Okay. Now, when two devices try to drive SDL to different values, there would be actually a conflict. Okay. So, what it is done is, the device can listen to the bus to be sure that it is not interfering with another message. Okay. That means, if a device is trying to send a logic 1, but hears logic 0, it will immediately stop transmission and gives the other sender priority. So, the moment it detects a conflict, okay, it would withdraw. Okay. The whole logic, the hardware should be built in such a way that when the device is withdrawing, it is not really disturbing the data which is passing on the bus. And after some time, again it should be tried out. This is the basic scheme of the bus arbitration. So, if you look into it, that this whole arbitration implies that there is a synchronization with respect to SCL, okay, because all these decisions are being made with regard to your SCL and SDA lines. So, what is being shown here is the SCL and SDA line of the bus, and these are the data may be coming from two distinct devices. This is your data 1, okay, and this is from data 2. Now, what you are finding here is that the data, when it is going through at this point, both the devices are generating identical data, okay, corresponding to this clock. So, now since the data is identical, there is no way to detect a conflict. There is no way to detect a conflict. So, the other device which is sending it, it will not detect a conflict, and it may assume that the bus is with it only. Now, what happens is that when it comes to the next one, there also you will find no conflict. The conflict comes in at this point only with respect to this clock. Okay. So, here there is a mismatch between the data 2, which is currently driving the SDA line, and it is finding that this is the data is high. So, it cannot drive the line, and hence it would realize that there is a conflict and it should relinquish the bus. Now, obviously, this whole logic works out with respect to a synchronized clock, because all these transitions, I told you that data valid condition is when your clock is high. If the SCL is not synchronized for these two, okay, and if two devices start issuing non-synchronized SCL, then there would be a problem. So, obviously, bus arbitration requires a step for synchronization on SCL and then the arbitration on the serial data line. Now, I2C is available, the hardware for I2C is available in a variety of PIC microcontrollers, okay, in variety of microcontrollers and in PIC family as well. Typically, this MSSP module, which is there in PIC, provides a support for I2C. Now, the basic structure is that in the I2 MSSP module, you have got this I2C engine, okay. You have got these two registers, SSP buff, this is a register. So, this is the master and this would be the corresponding peripheral. Peripheral should also have the I2C engine, otherwise it cannot communicate following I2C protocol. So, it has got the control and the control logic as well as the action part. So, effectively this I2C engine implements I2C protocol in hardware. This SSP buff is a register that stores data sent or received on I2C bus, because there will be serial data. So, it has to be stored and buffered, and this control controls action of the device based on I2C instructions. Now, try to understand the difference between the functional role of I2C engine and that of this control. Okay. Because if you remember, I said that if I have let us say a data frame I have started, okay, and I want to read data, the master wants to read data. So, I2C engine will detect that this is a read operation, and depending on that read operation, the control logic has to be activated to provide data on the serial data line. So, this is this control logic. Okay. So, control actions of the device based on I2C instructions. In fact, in a more general case, if you remember, I said that I2C bus has been used as a control bus for connecting onto various peripheral devices. So, if the peripheral devices has got a set of commands, okay, then those commands will be transmitted via the I2C bus. They will be detected by the I2C engine and passed on to control logic, so that there can be device specific action. Okay. Now, the most interesting thing that we have seen therefore with respect to the I2C is that it almost provides all the capabilities that you typically find in a parallel bus, although the bus is essentially serial and based on just 2 lines. The basic point I was making is in terms of the footprint that is being satisfied in this case. So, on a board, if I want to connect my PIC microcontroller with say another device and use a small footprint PCB, a desirable feature would be to use I2C bus, because I have to just put in 2 wires to connect a variety of devices, a peripheral, variety of peripherals to my PIC microcontroller. Okay. And it has got the complete logic for bus arbitration, which you typically find in a parallel bus as well. So, what are the advantages? Advantages is good communication with onboard devices that are maybe accessed occasionally, because if it is being regularly accessed, okay, say a cache memory, obviously I won't like to use a serial bus because that would be delayed. But if you remember, I said that in PIC, E square PROM has got an I2C interface. Okay. Why? Because E square PROM will be typically a program which is stored, which may be downloaded onto a RAM for execution, or some bookkeeping data would be stored on the E square PROM. So, these are occasional reads and writes. Okay. It is not on a regular basis. Now, this bus is easy to link multiple devices because of its addressing scheme, and cost and complexity do not scale up with the number of devices, because you still continue to use simple 2 lines and you connect an additional device onto the bus. The complexity of supporting software components can be higher than that of competing schemes, for example, SPI. Why? Because you have a complete bus protocol starting from how the address has to be put on the bus, how the address is to be interpreted and made use of. Okay. So, the complexity of the supporting software as well as hardware may be a non-desirable feature with regard to a simple application. Okay. But the more important things is these which makes I2C more popular, and in fact, these software components, the implementation of software components are also facilitated by making appropriate hardware elements available in the hardware blocks providing the I2C interfaces. So, next we shall look at SPI, which we say is a competing serial interface, and this is called serial peripheral interface. Okay. And in fact, it was defined by Motorola, okay, and it is now again available and can be implemented on a variety of these microcontrollers, including your PIC microcontroller. It is generally faster than I2C, that is capable of several Mbps, and applications is like I2C used in E square PROM, flash, real time clocks. and it is better suited for data streams like your ADC. The basic difference is it has got a full duplicate capability. In case of I2C, it is a half duplicate because I have got a single data line. Okay. So, it has got a full duplex capability, that is, and therefore, it can be used for maybe a communication between a codec and digital signal processor. Okay. So, let us look at this. Now, this is not like it is not using just 2 lines, but using 4 lines. There is a master, there is a slave. Okay. And what are the interfacing signals? This is the basic clock, this is input output. Okay. This is from master output and this is an input to the master. So, these are the 2 data lines, and that is precisely the reason why it is a full duplex mode communication. And there is another line which is called slave select. This is basically bar, so active low. This is a slave select line. So, using this line you select the slave. In fact, this implies that there is no distinct capability in the SPI bus configuration of associating unique addresses with the device themselves. So, synchronous serial data link is operating at full duplex. So, it is a synchronous bus, okay, because you have got a clock. So, it is a pure synchronous bus and synchronous serial data link, and it operates in a full duplex mode. The basic model is master slave relationship. Okay. In fact, there cannot be really multi master on this configuration. There are 2 data signals, this master data output, slave data input, also called SDO, serial data output, and MIA, so master data input, slave data output, also called serial data input. It has got 2 control signals, one is obviously the clock, other is that of selection of a slave. So, it's an active, it's a logic line, active low logic line, and there is no addressing, the point I had already told you earlier. So, now if we compare the 2 for point to point, if you look at SPI is simple and efficient, less overhead than I2C due to lack of addressing, and plus SPI is full duplex. So, it can be much faster than that of I2C. So, for multiple slaves, each slave needs separate slave select signal. This implies that there will be more effort and hardware cost on the master itself. Okay. So, you can realize that here the whole approach is that I am trying to get fast data transfer to slave devices or from slave devices, and there is no provision of a slave taking up the role of a master at any point in time. So, the basic configuration in this case would be therefore something like this. Okay. So, you have got an SPI master, and the interesting issue is that in this case I have got multiple slave select lines. Okay. Just like if you remember that when we talk about interfacing memory, okay, what happens when we interface a memory? I put in a decoder. In fact, we have seen that in the context of parallel buses, we have a decoder where we feed the address, and decoder generates the chip select signal by which I select appropriate memory block, okay, and then I refer to a particular location in that memory block. Here is actually master needs to incorporate a similar kind of a decoder. Okay. So, master would know the address of the slaves, okay, and it would provide in the software the address to the decoder, and decoder would generate appropriate slave select signal which would flow into the slave, and so that they are selected and they are able to respond to whatever is coming from the master. Okay. So, in this case the entire onus is on the master, and the hardware complexity of the master can also go up if it needs to interface multiple slaves. Now, so here it is not truly speaking, if you look into this is not truly speaking a bus. Okay. Although we are comparing with I2C, I2C is a bus. Why? Because I said there is a typically bus has one feature is that of a set of signal lines and number of devices being connected to that set of signal lines. Now, here all the slaves are connected to the same 3 signal lines, but each of them have their own private slave select line. Okay. In that sense, it is not strictly a bus. Okay. These 3 signals are same, but the select option is different, and here therefore, you have got distinct slaves related to the master. So, if I have a problem of interfacing a device, and when I know this device will be always a slave device and it is not likely to become master, okay, to take up a basic job of initiating a transfer of data on the bus, then I would select SPI as a protocol mechanism, because it enables me faster transfer. Okay. But when I need to connect multiple devices with a controller or a microcontroller, where I know that these slave devices have the capability to become master, and I would like this capability to flow to the slaves. So, there can be even data transfer between 2 peripherals directly without involving even the processor, then I would like to select I2C as a preferred option. This is a very key point to remember when you are designing a system based around microcontrollers like PIC, which provides support for both I2C as well as SPI. So, let us now look at the details of SPI protocol. Okay. So, this is the clock, okay, and what we are telling is I have got a rising edge mode of the clock. In fact, interestingly, I can define what kind of clock would be used for synchronization on the SPI bus by using basically 2 parameters, what is called clock polarity and clock phase, which determines the active edge as well as idle state of the clock. Now, this is a rising edge mode. So, this clock is, so all these data valid conditions would be with respect to the rising edge of the clock, and I got to have my slave select signal active for any kind of data transfer to take place. And this is a sample input. So, you have got again the same condition that you start with MSB first, okay. Just like in I2C, I had the most significant bit sent first, here also the most significant bit is sent first, and the entire sampling or the data valid time is defined with respect to the rising edge of the clock. In fact, this is a kind of a convention or a combination which SPI specifies and talks about. Say 0 0 is a rising edge, 0 1 all these are falling edge, and corresponding to these combinations there will be definition of the idle state of the clock, okay. And that is why these combinations define 4 distinct specification of clock. Okay. And the master and slave must agree on these parameter pair values in order to communicate. Okay. Otherwise, the slave won't understand whether you have got a valid data or not. Okay. So, in a way, what it implies is that when multiple slaves are getting connected to the master, master would need to know with reference to the slave what is the convention to be followed. Okay. So, if you have a master hardware, the master hardware should have provision of specifying these 2 parameters. So, SPI interface defines only the communication lines and the clock edge, and there is no specified flow control, no acknowledgement mechanism to confirm receipt of the data. So, if you want to build up that mechanism or the protocol, that is up to you. So, if you have designed a peripheral with a certain kind of an acknowledgement scheme, then you need to write the software on your microcontroller to make sure the whole transfer is conforming to that protocol that you have designed. Please note this, because in an I2C I have a basic protocol already specified as part of the standard, where I have got definition of a frame, that is start, stop, we have got definition of acknowledgement. So, that flow control is part of the I2C protocol. Okay. In SPI, it is just definition of the communication lines and the clock edge. You are free to develop your flow control protocol and implement. So, in that context, your hardware realization, the basic hardware realization can be done with a simple shift register. Okay. If you see, because shift register, why? Because it is a serial input output. So, if you look into here, you have got the SPI clock generator, and this SPI clock generator would come from the always master, because master is driving the bus. Master would need to know that for a particular slave, what kind of clock configuration is defined by those 2 parameters that I had earlier discussed. So, it will generate the clock, and depending on the data which is getting generated, okay. So, either it will be, if the slave is generating the data is shifted out by the clock, okay, and the data is coming here. This shift register is also effectively clocked by the same clock, and so the data would be ready. In fact, this is a very straightforward way. If I continue to use it indefinitely, then the same data will go from master to slave and from slave back to master. But in a processor, its implementation requires certain support. So, PIC provides that support for this processor, for this protocol. In fact, there is a SSP protocol and SSP module as well as MSSP module in PIC, through which you can really implement SPI. MSSP is I2, can be used for implementation of I2C also. So, in fact, using a PIC, if you are using that version of PIC which has got both SSP and MSSP protocol, you can set up an I2C bus, connect a set of peripherals via I2C bus, as well you can connect specific devices via SPI protocol using maybe SSP module. Okay, when there are a number of IO devices is to be connected, then you can adopt this kind of architectural model. The 2 basic registers, other than other registers, data registers which are involved, the 2 basic registers which are involved in PIC for managing your SPI is SSP con, this is SSP control register, and SSP stat, SSP status register. The sum bits which are used are, one is SSP overflow. Okay. If there is a buffer overflow, If you have seen, then a shift register, if you do that kind of a connection, there won't be any at any time buffer overflow, because data is flowing from master to slave and back to the master, but really I have to store the data in a shift register. And if that shift register is not getting cleared, the problem is there will be an overflow. So, the system should have an ability to detect whether such an overflow is occurring or not. So, a bit, that SSP-con bit, indicates whether there is a serial port overflow. Then you have got this enable bit. In fact, if you want to implement your SPI, okay, you have to first enable the synchronous serial port. Only when it is enabled, the whole implementation can really work. Then you have got the two bits, one is your CKP, which is clock polarity, another is CKE. Now, this is in SSP stat register clock edge select, and this is also the buffer full indicator is also there in the SSP stat. So, obviously, depending on the slave and depending on the modality that the slave is expecting, okay, the modality that a slave is expecting, you have to set CKP and CKE bit for doing any kind of data transfer. So, again these registers are involved. This SSP buff register we have already seen earlier in the context of I2C, the same registers are involved, and this is a control logic which would generate the clock, and it has to also generate the slave select signal. Okay. So, what we have got here is SSPR, these are now shift registers. SSP buff was a buffer register and it is not a shift register. Okay. So, the shift register is loaded by SPI data, okay, when the data is being received, and when the data is being sent, the data has to be loaded in parallel onto this shift register. And your serial buffer, this is your SSP buff. Okay. Now, the data is put here after an SPI transfer or before SPI transfer. That is from in this case what you see, which is interesting to note, is that once the data is loaded onto the shift register, the loading of the shift register will be guided by the clock. Once the data is loaded onto the shift register, it is transferred to SSP buff. So, it is a kind of a serial in parallel out operation. Okay. When you are actually transmitting, the processor will load data onto SSP buff, okay, and then SSP buff will load that data onto SSP SR. So, it is parallel out from here and parallel in to SSPR, and then it is shifted out when the data is being sent. Okay. So, this is the basic mechanism involved here. With regard to the device or the slave, I have also shown existence of similar registers, whether they are named SSP SR or SSP buff or not, they will have the similar capability. I got to have a serial shift register to get the data, and from there it has to be loaded in parallel to a buffer register, and vice versa for the purpose of transmission. So, therefore, what we have seen so far is mechanisms for connecting peripheral devices to the processor using serial bus. Okay. I2C is a true bus which can be a multi-master bus. This is SPI is a bus where I connect one device to the processor. There may be multiple devices to be connected, but each of the device which are being connected will be slave. They cannot take up the role of the master, and each device is being selected by a dedicated slave signal. Now, we shall take our attention to a slightly different problem. Okay. So far, what we have looked at in terms of parallel bus as well as the serial buses, the problem of designing the embedded system and how to use bus inside an embedded system. Okay? Fine. Now, the problem is, once I have made the embedded system, I need to communicate with that embedded system as well. Okay? So, how that protocol is to be defined. Fine. So, we go into another domain. So, we talk about what we call communicating with embedded systems. Now, obviously, this communication means that there will be a kind of a host, and we are talking about communicating with embedded system with the host. What is the other possibility? Other possibility is there could be two embedded systems, and I might like the two embedded systems to communicate with one another, a kind of a peer-to-peer communication. Now, there are various modalities by which this communication can take place. If we are going into a complete network based protocols, we can use that network based protocols for communications. I can have embedded networked devices, that is embedded devices where the complete networking protocol is enabled. Now, before going into the network issues, we shall address network issues later on in this course. Here we shall look at specific protocols which have some characteristics of the network protocols, but not really full-fledged network protocols which are being used for this kind of communications. USB is one such protocol. In fact, USB is another serial protocol, and also it defines the physical link. Okay. Now, it transmits all data differentially on a single pair of wires. Okay. And there is another pair which provides power to downstream peripherals. So, this bus also delivers power. So far in the buses, we have not really talked about power delivery. And in fact, the whole development had been with keeping PC as a core host. Okay. So, it is basically PC centric protocol, and in a way every USB device is an embedded system. Even the flash disk that I am putting onto my PC, it itself an embedded system with a small processor sitting in it. Okay. So, why we need to know therefore the USB protocol as an embedded designer must be very clear, because if I am trying to design an embedded system and I want to provide that embedded system the facility to communicate with hosts, it should be enabled with the USB protocol. So, the basic concept is that of a bit serial bus. Okay. Now, this bit serial bus which uses differential drive technology is distinct for USB and different from that of your I2C or SPI, because I2C and SPI was primarily on board specifications, that is typically on a single PCB. When I am trying to put different devices, I would connect them using I2C or SPI. Now, these are kind of external bus definitions, so external devices are to be connected. So, I have got the differential voltages which are between these two lines, which would define the bit levels high and low. Obviously, it would be much more robust and signal to noise ratio would be better compared to that of a single wire bus. Typical speeds, it is a high speed bus between in fact, if it is a high speed, it is 480, in fact 12 MB it can go up to, the lowest speed is 1.5 MB. Signals are basically V bus, okay, that is this is basically the power signal and the ground, okay, and the other signal is basically D plus and D minus, these are the differential levels for communicating the data. what we say that USB devices can pull a limited amount of power from the bus. If a device requires additional power, it may be connected to a power line, but if it is not so, it can be drawing power from the bus itself. So, my flash disk which I connect, which does not need additional power, is actually drawing power from the bus itself. And system may provide a power management protocol, in fact which is independent of the USB. What would be the basic motivation of this power management protocol? If the device is not being used, shut down the power to it, so you actually save power in the process of communication. What is the basic USB architecture? USB peripherals are slaves which typically respond to commands from the host. So, I told you this is a host based structure. So, there is a host and these are all slaves. When a peripheral is attached to USB network, the host communicates with the device to learn its identity and to discover which device driver is required. So, this process is called enumeration, and this enumeration process is supported as a device driver for the USB port on the host or the master. So, obviously, the architecture wise ideally do not have what is called a multi-master. Okay, I have only one host and a multiple slaves which can be connected to the bus. The USB devices are typically of two types. One is called standalone, which has a single function like that of a mouse. There may be compound devices, those that have more than one peripheral sharing a port. Typical example is a video camera, because it has got a image capture device, it has got a audio process device. So, it has to send both image as well as audio via the USB link. So, they are compound devices. In fact, USB distinguish between these two distinct types of device. The basic organization is what is called a hub based organization. So, you have a host device. So, to a host device you can connect a hub and your peripherals gets connected to the hub. Otherwise, you connect a single peripheral with the host device. Okay. So, I can build now a tree. So, if I connect at one port another hub, so I can connect more peripheral to this, and that is why this is called a bus. Okay. That means there can be multiple devices hanging from one link. And these USB hubs are nothing but bridges. Okay. Bridges we have already studied in the context of parallel buses, they are very, very similar to bridges. So, it increases the logical and physical fan out of the network. A hub typically has a single upstream connection and many downstream connections. So, these upstream connections connect the hub to the host. It may not be directly communicating in the host, but it may be communicating with the host through another hub. Hubs themselves are USB devices, and hubs have the ability, which is not there in all USB devices, to detect topology changes due to insertion or deletion of device. Okay. And they are also source power to USB network, because the power has to flow further down. So, this gives us more or less the architecture of the USB. It has got a definite protocol for doing the data transfer, which is much more sophisticated than that of typical I2C kind of a protocol, because you are now communicating with embedded systems, and each of these systems have got actually the capability to run this whole protocol machine on its processor. Okay. So, it is just not as simple as FSM implemented in the hardware the way it is in for I2C. Here you have got processors involved, maybe at the various devices, so you can have a more complex protocol scheme. So, this brings us to the end of today's discussions. So, we have studied serial interfaces like SPI and I2C for connecting peripherals to the basic microcontroller blocks, making an embedded system. Then we have started looking at the protocols which can be used for connecting embedded systems to hosts and other embedded systems. We have studied architecture of USB. We have not really looked at protocol of USB. We shall look into protocol of USB and other similar protocols and interface mechanisms in the next class. Any questions? See, these are the two parameters. The question you have asked is what is the significance of clock polarity and the clock edge parameters. See, if I have a clock, now with regard to the clock, whether the transitions, that is the data, I have the data line. So, whether the data on the data line should be valid with respect to the rising edge or falling edge can be configured. Okay. So, that can be done with regard to the clock edge. Now, with regard to the polarity, what we can do is, now polarity means whether high is an ideal state or low is ideal state. Okay. So, therefore, using these two bits, these combinations can be identified. Okay. These combinations uniquely configures the clock signal for a slave device. So, that is a facility that SPI provides for.